All right, today's lesson, we're going to talk about section 6.2, which is the natural base e. There's this number e that tends to come up when we're talking about exponential and logarithmic functions. So in order to figure out what this number e kind of represents, we're going to do a little exploration with some interest. So this first part, it says, consider an account where $1 is invested at 100% interest for 1 year. What would the value of the account be if the interest is compounded weekly, daily, hourly, or 1,000,000 times per year? How does that kind of value of the account change? So we're going to go ahead and do the calculation. First, if we are thinking about weekly, that means n is 52. So if we're looking at all of our values, we have our P, our principal is that $1. Our rate, it says, is 100%. And 100% as a decimal is just 1. And then it says 1 year, so our time is 1. And if we're talking about weekly, our n is this 52. So we're looking for the first value in our table. If I use our equation from last time, we're putting $1 in, 1 plus, we have r over n, so 1 over 52. Raised to the power of the nt, so 52 times 1. So if I plug that in to my calculator, figure out what value we get, I'm going to get 2.6926. Saying if I invest my $1 at 100% for 1 year, and I'm compounding weekly, I'll have $2.69 after that year is up. Okay, what happens if I compound daily? So if I'm compounding daily, my n value is now 365, so our second value of the table. I still have my principal is still $1. I have 1 plus that 100%, so 1 over the 365, and then raised to the power of 365 times 1, because 1 year. If I calculate that one, I end up with 2.7146. Okay, so after the year, my account has $2.71 in it. What if I go more than daily? What if I go hourly? Okay, so if I'm talking hourly, I need to know how many hours are in 1 year in order to figure out what my n value is. So there are 365 days in a year and 24 hours in each day. So if I multiply 365 by 24, I get 8,760 is my n value, how many times I'm compounding in a single year. So I'm going to have 1 plus 1 over that 8,760 raised to the power of 8,760 times 1. If I plug that in, we get 2.7181. So still pretty close to what we had, $2 and maybe like 72 cents, but it is getting a little bit bigger. And then our last one, what if I'm doing 1,000,000 times per year? So instead of weekly or monthly or hourly, we're doing 1,000,000 times per year. So my n is going to be 1,000,000 times. So I still put $1 in, 1 plus 1 over 1,000,000 raised to the power of 1,000,000 times 1. And when I do this calculation, I get 2.71828, and it goes on. And if we continue in this way for 1,000,000,000 times, 1,000,000,000,000 times, even more and more, as we get more and more compounds, what we're seeing is this value. We started with our $1, our y-intercept is $1. And as we're compounding, this number gets closer and closer and closer to an asymptote, a vertical line, which we call e. And this value e actually is like this kind of weird, crazy number. It is an irrational number. You can kind of think about it like pi, in that it's this number that we know, but it goes on forever and ever without repeating, without like a pattern necessarily, and it's going to be this number. So even though I made it kind of stop there, it really goes on forever, lots of digits. As we get closer and closer and closer to infinity number of compounds, we'll get a number that has more and more decimals. Okay, so what do we need to know about this number? The value itself, I'm going to give you the value on a quiz or test, but there is a button on your calculator that says e to the x, usually kind of looks like this, e to the x. And if you just want to know what e is, you put e to the first power to kind of determine what value we have, but that is on your calculator to click. Okay, for the ones down here, kind of the purpose of this next section, natural base expressions, is just to apply our properties of exponents or roots, radicals, to these expressions with e. Okay, so the first expression we have is this e cubed times e to the sixth. And when we have numbers that have the same base and we are multiplying those values, we can add their exponents. So this is going to be e to the 3 plus 6, or e to the ninth. All right, for number 2, we are dividing these things that have the same base. So if I have e to the 5th over e to the 4th, I am subtracting their exponents. Also, we want to think about the coefficients out front. That's 16 over 4. Those are the coefficients. I can reduce that fraction just like I do any fraction. So 16 over 4 is just 4. So I end up with 4e. It's really e to the first power because 5 minus 4 is 1. And we don't need to write a 1 as a power. It's just kind of understood. Number 3. I can either start off kind of dealing with this negative 4 exponent, or I can distribute the 2. It's kind of our choice. Either way, we're going to end similarly. So I'm going to go ahead and distribute the 2. And so I have 3 squared. And then I have e to the negative 4x squared. That squared does apply to both parts of the things in the parentheses, both parts of that factor. So 3 squared is 9. And then e to the negative 4x squared is going to be e to the negative 8x, because we are multiplying when we have a power of a power. But we're not allowed to leave something with an exponent that is negative. Okay, an exponent that is negative means it's the reciprocal. So we want to change this to 9 over e to the 8x. Okay, the 9 does not have a negative exponent, so the 9 stays in the numerator, but that e to the 8x is going to move to the denominator. Last one, we have a square root. And here you need to remember that a square root really represents a 1/2 power. So I have this expression to the 1/2 power. And when I write it like this, it's kind of easier for us to think about distributing the 1/2 to both. And so I have 9 to the 1/2 power and e to the 2x to the 1/2 power. Well, 9 to the 1/2 is the same thing as the square root of 9, and I get 3. E to the 2x times 1/2, I am multiplying that 2x times 1/2 because it is a power of a power, and I get just e to the x. Okay, so we still need to remember our properties of exponents and of radicals as we move forward, whether it's a base of e or a base of 7 or a base of anything that we deal with. Next up, we're going to talk about graphing these natural base functions, and they still are exponential functions. So it says here, the general form of a natural base exponential function is this y equals a times e to the rx power. And what we see here is that that a value is still our y-intercept, or our starting value, and the b value that we normally thought about, the b value from yesterday's work, e to the r power is our b value. So it's either our growth rate or a decay rate, decay factor or growth factor, depending on if that r value is going to be an increase or a decrease, a positive or a negative. So we can't just look at the E itself. It's E sometimes with some rate associated it, because we're saying like it's growing at 5%, but with this E in there. Okay, so looking at the just general form, we're going to see exponential growth, exponential decay. This first one is exponential growth. We just have y equals e to the x. Here our a value is 1, and that's where we see this y-intercept of 1. It's kind of like there's a 1 in front, the coefficient. E to the x is saying our b value is this e, which is about that 2.718 value. And so we can kind of see that it's here, that we're multiplying our function value by that. It's the growth. For decay, here they've written it a little bit differently than we saw it yesterday. So when we have y equals e to the negative x, we still have 1 as our y-intercept. So a is still 1, but b is e to the negative 1. Okay, we kind of have to look at this portion of things as our growth or decay factor. And when we have e to the negative 1, remember that is like 1 over e. It's the reciprocal of e. And 1 over e, we're saying like 1 over this 2.718 number is about 0.368. Okay, and because that number, that 1 over 2.718 is less than 1, we get this 0.368. 0.368 is less than 1. That's why we see decay here. Okay, so in general, if we have a negative exponent associated with our function, this negative exponent here in our equation, we're going to end up with a decaying function, because it's going to be like a 1 over e, which gives us some value between 0 and 1, which means we have decay. Okay, we're going to graph some of our own on this next page. So graphing exponential growth, just like we graphed last time, we want to identify our y-intercept and maybe how it is growing. So looking here, the 3 represents our y-intercept. We can put that in our table as 0, 3, and on our table, and on our graph as 0, 3 there. To find the other values, we want to plug in different x values, or we can also use the fact that we're multiplying by e. Okay, that b value is e. So we're like multiplying by e to get there, multiplying by e to get there. Now, e is the strange number, but we are going to be able to do it in our calculator. So if I want to find 3e to the first power, I'm plugging in 1 into our function. I'm going to use my calculator, plug in 3e to the first power, and I get 8.15. I'm keeping 2 decimals, but this goes on. If I plug in 2, I get 3e squared. Well, 3e squared is like 22.17. Kind of big. It's going to go off our graph. Likewise, if I plug in some negatives, 3e to the negative 1 power. Well, negative 1 power, remember, is the reciprocal. And so it would be like 3 divided by e. But you can also just plug it in just as it is, 3e to the negative 1. And your calculator should give you 1.10. And if I plug in 3e to the negative second power, plugging in that negative 2, I get 0.41. So let's go ahead and graph some of these points. We started there with 0, 3 in the middle. If I graph 1, 8.15, just doing my best to get close, The 2 comma 22 is off my graph. I'm not going to be able to show that one. -1 and 1.10, and then -2 and 0.41. We have those values. I want to kind of sketch our graph coming through there. And we see that it is growth. And this growth is even stretched out a little bit because of that 3 in front. That's like our stretch or shrink, but in this case, vertical stretch of 3 of that function before. So it's this same function stretched by 3. Okay. For the exponential decay, this time we have e to the negative 0.5x. So where this one was like negative 1x right here, like negative x, now I'm doing 0.5. So I'm actually kind of squishing things or stretching them out in a horizontal way because it's working with the x. We can just graph the points and see what's happening. So start with our y-intercept, and here we don't really see a number in front of the e, so it's like a 1. So we have 0, 1 on our table and on our graph. Okay, to get the other values, we're going to plug into our calculator, and notice here they gave us a few table values that are different than the previous one, but we can just plug them in. So if I plug in 2, I get e to the negative 0.5 times 2. E to the negative 0.5 times 2. That's that 0.5 times 2 is all up in the denominator, up in the power. And so if I calculate that, I actually get 0.37. And if I plug in 4, e to the negative 0.5 times 4, I get 0.14. Moving to the negatives, if I plug in e to the negative 0.5 times negative 2, it's really like e to the first. So I get this 2.718, I'm just going to go 2.72, but it is this value of e. And then e to the negative 0.5 times negative 4, I really get e squared, which is 7.39. And let's graph some of those values. 2, 0.37, 4, 0.14. Those are really tiny next to the axis there. Going backwards, negative 2, and then 2.72, and negative 4, and 7.39. And we can show our curve. Notice this is decaying over time. It is going from high to low, kind of that decay happens because our e to the negative 0.5, this number is between 0 and 1, so we have decay, so that we're seeing this graph decay. All right, so you need to be able to take this equation, get values, and plot those points to find the graph. You're going to need to be able to identify the A value, which is the y-intercept, and the B value, which is that growth or decay factor, depending on what's there. Okay. The last section we're going to talk about is compound interest, but this time it is compound interest that is compounded continuously. So we see that word here, compounded continuously. If you remember last class, we talked about the formula. If we have a certain number of compounds, so if they tell us that it is compounded n times per year, we have a certain number of compounds. We're going to use that formula from last time. But if they tell us it's compounding continuously, they use that word continuously, that means it is compounding really like an infinite number of times. It's not even like countable how many times they're doing it. They're compounding and compounding and compounding more than a million, more than a billion, like an infinite number of times. that is when we're going to use this new formula. A equals P e to the RT. Okay, so anytime we see the word continuously compounding, we want to associate it with this formula. This will be given on your assessments. Okay, the values of the different parameters are the same as what they were last time. So our A is still the account balance. The P is still the principal, or what we put in. The R value is your interest rate, and we do need it expressed as a decimal. And the time, T, is time in years. Okay, so those same 4 parameters are still in this formula. The only thing we are missing is the N, because when we're saying we're compounding continuously, it's like an infinite number of times, and so I can't plug in infinity. All right, number 7, let's actually use this. It says you and your friend each have accounts that earn annual interest compounded continuously. Find the balance A in dollars of your account after 10 years, or this balance can be modeled by A equals $4,500 times E to the 0.04t. Okay, so this is your account. It says the graph shows the balance of your friend's account. So you have an account, your friend has an account. Yours has a formula, theirs has a graph, and we want to compare them. So the first question they ask is, which account has the greater principal? So remember, principal is the amount you put in. If we're looking at the formula for yours, looking at this formula, the $4,500, that is how much you put in. Notice that's like what's in that P spot. So in your account, you put in $4,500. In your friend's account, how much did they put in? When I go to my friend's account, they don't give me an equation, so I can't just pull it out like where's that P principal. But when we're looking at the graph, the principal is the amount that you start with. It's the value, that starting value. It's how much you put in there. And so your friend starts with $4,000 in their account. So that is called the principal. So which account has greater principal? Your account does. All right, the second little part says which account has a greater balance after 10 years. So if we're talking 10 years down the road, your account, in order to find it, we're going to have to plug in T equals 10. So we have that 4,500 times E to the 0.04 times 10 up there in the exponent. So E times 0.04, or E raised to the power of 0.04 times 10 times, like I said, that 4,500. We end up seeing that your account balance after 10 years would be $6,713.21. What about your friend? Okay, again, we have to base the friend's information on the graph. And so what is their balance after 10 years? And 10 years, if I'm looking on that t-axis or x-axis, put a 10 there. And if I come up to my curve and then come over here, we find that my friend, well, it's real hard to kind of see what they have. It looks like it's between 7,000 and 8,000. I'm going to say with like about, and this is a real hard guess because you have to kind of get there, maybe like 7,400, but that is like an about. What I can tell you is it's definitely bigger than 7,000, because 7,000 would be right here in the middle line. And this is bigger than that. So your friend's account has the bigger balance after 10 years. That they have 7,000 plus 7,400, maybe 7,300 somewhere, but your account only has $6,713. Okay. Number 8, it says you now deposit $4,250 in an account that earns 5% interest compounded continuously. Compare the balance after 10 years with the accounts in problem 7. So if this time, your new account, you are going to deposit $4,250 in an account that earns 5% interest compounded continuously. We need to write our own function using this equation, A equals E, P E to the RT. So we're going to have A equals, we have $4,250. E, since it says 5%, remember our R value would be 0.05 in that power. And then it does ask for 10 years. So my T is 10, so times 10. So I want to find what's the balance of this account after 10 years. I'm going to plug in this value, calculate, and I get $7,007.07. Okay. So the question says compare the balance after 10 years with the accounts above. Remember, your original account made $6,713. Your friend's account was about $7,300, $7,400. And now this one is $7,007.07. So I think this one to compare would be in the middle of the two other accounts. This value is between the other two accounts. Of comparing to what we already have accounts. And then last one is kind of a fresh problem. It says, how much more money does this account earn after 10 years with interest compounded continuously than with interest that would compound monthly? Okay, so this value, this $7,000, I don't even know what I'm saying, $7,007.07. This is with the continuous compounding because we use the E as part of our formula. They said they want us to compare that to what if it is compounding monthly. If we are compounding monthly, we need to come up with a formula that includes an N value. So we need to go to the original formula we learned last class, which is that A equals P, 1 plus R over N to the NT. So we're going to have A equals, we're still putting in $4,250. We are not using the E. We're going to have 1 plus, the R value is 0.05%, so 0.05, divided by 12. 12 is because we are doing monthly. And then 12 times 10 up in the exponent because we are compounding monthly for 10 years. So 12 times 10 up in the exponent. And if I compute this, I get $6,999.79. Okay, so if I'm compounding continuously, I have that $7,007. If I'm compounding monthly, I have this value, and it says to compare them. How much more money does the continuous have than the monthly? So I'm going to subtract 7,007.07 minus the 6,999.79. And if I subtract those two values, I actually only get $7.28 more.